Okay, so welcome everybody. This is the 18th of November, 2025. This is Open Research Institute's projects meetup. What we do at this weekly meeting is we talk about what we've done, what we plan to do, if we need any help, any resources that ORI can help you get, and if there's any roadblocks in your way. So this is a sort of a roundtable format. And then we sometimes have folks that come in and tell us about their particular project and do a deeper dive or try to solve problems in the meeting. So first we do the roundtable, and I'm going to turn it over to Paul. So you have the floor, sir.
Okay, good morning, or whatever time it is where you're listening. Um, I've got a few things to show. These are actually from last week, I think, but then I'll talk about this week. Let's see if I'm going to be able to share my screen. No, one of those a whiteboard.
Okay, let me fix that, and then we can swap the whiteboard. We'll swap the whiteboard back in later. So let me make it to where you can share. Okay, it's all you, sir.
Okie dokie. Okay, this is a visualization that I've been using when we were debugging the FIFOs. We got Matthew to insert some code into the HDL to give us a register where we could read back the FIFO pointers. There's four of them: transmit and receive, FIFO, and then each FIFO has a read and a write pointer. And this is where we were November 4th or thereabouts. Uh, Black dots represent the transmit write pointer, red are the transmit read pointer. And then the green is the receive read pointer. And you won't see any blue dots. Well, there's a couple down there in the lower left-hand corner. Maybe. No, I guess not. Because they're all under the green dots. So you can assume that that's both the read and the write pointer for receive. So what we see here is things not quite working correctly. You can see that at startup, at time equals 0 across the bottom. The transmit read and write pointers are different. They start at 0, but or near 0 anyway. But the transmit one fills up like crazy before anything happens with the receive with the read pointer. So there's this big gap between the two, black line and the red line for a while, and that's an initialization problem pretty clearly. And then sometime around time equals 370, it just stops. And that happens to coincide with when the right pointer wraps around, suspiciously enough. So these are extremely useful visualizations. It's hard to winkle this kind of understanding out of the plain log file. You have to stare at it and squint and maybe take some notes. But with a graph, you can really see what's happening. The green here shows um, m more reasonable behavior. It starts at 0 where it's supposed to, and then it um, every 40 milliseconds plus or minus we see a frame worth going through the system, so that's good. Um, this is sampled from a separate thread at about a 10 millisecond spacing, so this is not extremely detailed information, but it's not tied to any particular event going on in the code, so it's really time. So we spent a lot of time with this after evaluating a bunch of graphs of this sort and going back and forth and iterating. And we finally got to um, this picture. Um, this is actually pretty darn good. Um, what's going on here is that I start the test and capture some data. And then when I get around to it at around 4,000 milliseconds in this picture, I start a voice transmission. That's the easiest way to send continuous frames. And then let that run for a few seconds, and then somewhere around 10,000 or so milliseconds, I stop the voice transmission, but I'm still capturing. So take a look at the red and black first. They sit down at 0 where they're supposed to be because I'm not actually transmitting yet. And then as soon as I start transmitting, the black dots start coming out like clockwork you can't really see that it's like clockwork in time here because I've zoomed way out to show the whole test. But by zooming in the graph, you can see that these are 40 milliseconds apart, just like they're supposed to be. You can see on the vertical axis that they're 1 frame apart, just like they're supposed to be. And the red, um, remember that's the transmit read pointer, is not jumping frame at a time. It's metering out the data little by little, which is what we expect to have happen. Because that's how transmit works. It's sort of a bit at a time kind of thing, which translates up to IO as a byte at a time. So as we sample the FIFO, we'll see it drain uh, little by little, but it never gets very far away from the black line, so there's not a lot of extra latency added, and it goes pretty much like that through the whole test. Uh, Pretty nice. And then around 10,000, it stops, and the read pointer stays consistent, and the right pointer, I think I trimmed out manually of this graph, so you can't see it because it didn't really matter anymore. And then the green, during the portion of the test where I'm transmitting, it's also clocking along. You can see there's a couple of frames of latency, um, but it uh, is putting out a frame of read every uh, of received data. This is on the RF loopback. It's receiving a frame every 40 milliseconds, just like it's supposed to during that transmission. And what you also see on either end of the graph here is the receiver randomly picking up what it thinks are frames. So over here on the left-hand side, you see a frame coming around time equals maybe 250 or 300 uh, milliseconds, but there's not really a frame there, so it just sits there. And then again, around 500 or so, or around about the same time because it didn't sit there for very long. Anyway, we've got all these random length green lines that represent frames that were detected mistakenly. Um, and they would have been fed through because they look like frames to start with. It's a sync word being detected. And then immediately the next frame along, you'll find out that, oh, that wasn't really a frame because I didn't get a second sync word or a third one or a fourth one. So we're getting a lot of these. I'm not sure that this is normal. We'll have to run the numbers to be sure. And it happens again after the transmission stops. You can see that the receiver continues to put out some gibberish after the transmission. So this is where we're at right now with the frame-based thing, and this is pretty good. I think this can be made to work. Um, so that's like a week's worth of progress from last week. And when we have all this stuff working correctly, then I'm going to change what I'm sharing here for a second. This is a recording of what the spectrum looks like now. Um, we have added our timeline management. So frames are coming out at the right time and never getting dropped there. And in addition to that, the bits that are being transmitted have the scrambler attached. So we're transmitting more or less white data. And doesn't that spectrum look pretty? That's pretty much what it's supposed to look like all the time. You can see the tones starting to peak out a little bit in the main lobe, but everything is pretty round and continuous and lovely. So I'm very happy to see that spectrum come out of the frame-based um, code. And that's all I'm going to share on the screen right now.
Okay. Thank you so
Uh,
much. Yeah, that spectrum is actually a really totally good indicator. The what we worked with initially was pseudo-random binary sequences. So we would feed in to the modem a binary sequence, like a deterministic, like we know what's going to come next. We've mathematically predicted it, and it's guaranteed to be close to random. When you have a random sequence that you're sending over the air, then you get the full spectrum. You get the outlines of the all the potential spectrum. If you send lots of structured data just over the air, then you'll get all sorts of weird peaks and stuff, and it's not as efficient. So that's one of the reasons why one of the stages of digital signal processing is to randomize or they used to call it whiten your data. Now we refer to it as randomization. This particular part of the process is you take a known sequence, a known, as random as you can make it, and you XOR your data with it. And then you XOR it on the other side to get your data back. And what this does is it takes data that might have long strings of zeros and ones, or a header file that always looks or header that always looks the same, and that will make your spectrum not quite as efficient as it could be. So, when you see this sort of spectrum, that's what it is about. Um, and the efforts to get kind of the FIFO to behave are super important because we need the first in, first out buffering to work right and to track and all the pointers to work right. And I think we're there. Over the past couple of weeks and over the past week especially, that is all working and is really great to see. And the one thing that you brought up that's very clear on your graph is that there's false alarms. So when we're sitting there as a receiver, what we're looking for right now is we're looking for a particular synchronization word. And this is 3 bytes that's always stuck on to the front of every 40 millisecond frame. And we look for this, and then we decide whether or not it's a frame. Now, we don't just take its word for it, because 3 bytes is only 24 bits. And that sounds like a lot, but when you have random data coming in over essentially the crash of static that is coming in from your receiver, you will get this sequence a lot. You'll get it quite a bit. And you can literally see that in the image that Paul shared. That's a really powerful image because it shows how many times your false alarm will go off in your synchronization word. So we have something for this. A very common tactic with digital signal processing is what's called a synchronization lock, where you've locked on to a signal. And this is a class we're talking about the frame level, not at the bit level. We've already demodulated bits. We already think that we have a signal. What we're doing is trying to figure out if we have a signal that makes any sense. And so we're kind of looking at what we have and we're letting it shift by us, and we're going like, okay, these 24 bits match our sync word. Let's see if in exactly 40 milliseconds we have another one. Oh, we don't. Okay, that was garbage. That was noise. False alarm. So we have a hysteresis curve, or a bar we have to get above. And we say, okay, did I see a sync word again where I expected it? Did I see it again? And then you declare lock. And then you can like kind of back off. You actually have real data. You can be confident of putting that downstream. In the reverse, we have the reverse situation. We have a lock, let's say for 30, 40, 50 seconds or many minutes or maybe an hour, we have a solid signal, and then suddenly we miss a sync word, because we're showing up every 40 milliseconds at the beginning of our expected frame. We're checking to make sure that the synchronization word is there. What we do is we say, oh, okay, oh, I lost it. Okay, did I lose it 2 times in a row? Now we go back to hunting. Now, instead of just showing up every 40 milliseconds, we show up every single bit. And we're now going to search for a new synchronization word. So it's a hysteresis curve in both directions. And that sort of stuff is working and implemented. Now, it could be optimized. Do you wait for 2 times, 3 times, 4 times? Those questions we'll have to answer a little bit better later. But Paul has just shown you that it works, and that you can literally see the false alarms. They come more often than you would think. The way around this is, you go, oh, is 3 bytes enough? The longer the synchronization word, the less likely that particular sequence would be seen in noise. So there's a trade-off here. How much overhead do you want to put into every packet just to make sure that you have a packet? And this is one of those really interesting things in comm theory. How many bits do you want to spend on making sure your signal's really resilient? And in the other digital communications modes that are in our ballpark, from P25 to System Fusion to some of the military modes, we're right in the middle, probably middle upper. So 16 bits up to 48 bits, which is really 24 symbols. So it would match up with our 24 bits. We're actually towards the high middle range in terms of the length of the sync word. So the false alarm rate might look disturbingly high, but if you just say, I have to get a few in a row before I declare a frame lock, and until then, I'm going to go ahead and pass along the data, then I think we're in good shape. This will need to be optimized and explained, but we're right there. We're doing really good, and I think we've delivered a good results. All of this is already in the code base and is already in the repository, um, and we'll move forward from here. Okay, back to you, Paul.
Thank you. One thing I have not graphed in this particular picture that Michelle was talking about is the signal strength. Um, I happen to know from recalling that in both of those graphs, in fact, the uh, the signal was very distinctly not there at the beginning, and during all those false alarms, we'll see the incoming signal strength as measured by the radio's receiver was like minus 120, which is nothing. There's no signal there. So it's not that it was false alarms in a sequence of bits that came out of a receiver. It's false alarms out of garbage coming out of a receiver. And
Right.
we can do something much smarter, much more effective, I should say, without being too smart in those cases by just squelching and not trying to receive data when it's not really there.
Excellent.
Um, and Matthew has promised us, or actually, he said no promises, but he's hoping to develop a good lock indicator for the physical layer that we'll be able to distinguish when he's demodulating absolute garbage versus just demodulating a real signal. And if we don't even try to look for frame sinks when there's no actual signal there, then that'll suppress the vast majority of these false alarms and make it easier for the downstream protocol processing to make sense of it.
Awesome. Yeah, thank you so much. Is there anything else that you wanted to bring up or add?
Yeah, I do want to talk about this week
Okay,
um,
go ahead.
that having achieved this level of workingness that we hadn't seen before, I decided to take a few days and address some technical debt that's built up. We've been doing all this in one giant C file and using a very simple command line script to compile it, and that's starting to get cumbersome. There's so much stuff in that file that it was hard to even know where to put new stuff or where to look. Search is great, but you still get some confusion when you have one big file. So I've spent some time dividing this up into many files. I'm not quite finished yet. There's still some dividing up to do, but I'm taking one file, one sort of subject matter at a time, like one thread or one data structure or one part of the radio, putting that into one file. And now I've got lots of files instead of just one giant file, although the main file is still pretty big because I'm not finished dividing it up. Now the script approach is cumbersome. So gone, I've advanced fully into the 1970s, I think, and I'm using a Makefile instead of a plain script. And as a sort of a side effect of going to the trouble to make the Makefile, um, it now also borrows a trick from the firmware and uh, embeds the git commit hash as a identification tag. I put it both in a define so that the code could print it out and also use it in the file name. So I can just look at a file name and see what version it was built on.
Oh, good.
And that will avoid one source of errors and certainly confusion that slows you down when in the lab. So I'm hoping will have been worth the trouble. We'll be done with this pretty soon. And the next phase is going to have to be uh, changing whether we're doing all the processing, namely uh, the whitening or the randomization, the forward error correction, and the interleaving that makes the forward error correction work. Whether we're doing that in software in Dialogus or doing it in hardware in the HDL. And up to now, have not had it in the HDL. And so what has been done of that has been done in Dialogus. We want to move toward more and more of that in the HDL, which I imagine Michelle will have a lot more to say about. But in the meantime, uh, I'm going to try to make it runtime switchable so that it could do either one with the same build. Uh, it won't be switchable on the fly. You have to decide at the start, and it'll be fixed. That's because the HDL is not going to change on the fly either. Um, so that's the sort of a branch that I've got working now, and it's going through that and looking at all the steps of dealing with the processing and the frame size switching in the software. Have identified some additional things that need to get attention and fixed up. So that branch is there. It's going to be parked for a while until I get these other things resolved, and then probably rebase it and merge and have that capability probably pretty quickly. I hope it's going to be a relatively simple thing to accomplish, and we'll be ready for what Michelle's probably going to tell you about modifying the HDL. And now I'm done.
All right. I think I'll take the opportunity to talk a little bit because it also has to do with what Martin's in charge of and leading. So welcome to Martin Ling, who is the lead for the Mode Dynamic Transponder project at AMSAT UK. And this is a FPGA-based project, and they have a different FPGA for the project kind of laid out. And so there's a lot of work that's already been done on the bill of materials and a dev board for investigation there. This is a future launch from AMSAT UK. It's the FunCube Plus, which is a follow-on project to the FunCube satellite, hugely successful amateur radio satellite project. And so what we've been talking about doing is helping Martin achieve his goals for sort of Earth observation and weak signal work, and also like what kind of modes can you fit into the ICE 40 from Lattice. And so when we talk about like the decisions on HDL and like what the processor side is or PS side is doing, which is what Paul's been talking about, like, all the programming and figuring it out, getting it to be efficient and work. And there's a big load balance decision. So, like, what does your processor do? And what does your FPGA do? And then the third leg of the stool is usually a GPU or a graphical processing unit. So if you want to get really super advanced into hybrid computing, then you would also kind of bring in a GPU. But for most of software-defined radio, for most advanced amateur radio projects, what we're dealing with is a software-defined radio that has a general purpose processor that runs C or C++ code or Python, and we also have an FPGA which handles hardware tasks. And deciding what belongs to the processor versus what belongs to the FPGA is one of the it's an enduring question. So I'm going to go ahead and I'll go ahead and share something, and then we can talk about uh, let's see, particularly the ICE 40. Like, is this working? Oh, so you should see like it looks like a very busy graph or table. Is
I
that
see it.
okay? Good. All right. So this is the utilization report from Vivado, which is what we mainly use for our mainly we use Xilinx chips. And this is a utilization report from our modem project for Opulent Voice. The first target is the Pluto SDR, which has a 7010. This is a Zinc device from Vivado, and it has a ARM processor and a lot of it's a we call it a fairly small FPGA, but it's really not. It's a decently sized FPGA, but it's small, in the grand pantheon of FPGAs. So here's the utilization report, and so right off the bat, the things that are notable here is that the MSK or the MSK underscore top is our name for our wrapper design. So minimum shift keying. So it focuses on the modulation. So when we talk about Opulent Voice, that's the protocol with all sorts of decisions about things that affect the user. But the actual like where the rubber hits the road is in the FPGA, and this is the modem. So the modem is a minimum shift keying modem that delivers the correct bit rate at the correct spacing for Opulent Voice. And right now, MSK top consumes about 5,200 LUTs. Okay, so in the Xilinx universe, it's you know, you have a total on the 7010 of 17,000. 5,000 of them are the MSK top. However, 2,300 of them, rounding up, are consumed by the configuration and status registers. 2 weeks ago, we talked about refactoring this because in development, you need access to registers. You need to look at everything. Everything gets a 32-bit counter or a register. So half of, or half of the 55,000 or thereabouts is in the configuration status register. Now, this is not ever going to go to zero because you absolutely have to have register access and to be able to configure, to be able to get status of what's going on with your modem. But when we talk about like how much does Opulent Voice really consume, then our custom logic that we have put into the reference design from Analog Devices on the 7010 for the Pluto SDR is about 5,000. Now, when we talk about the AMSAT UK effort and MDT project or mode dynamic transponder, and with an ICE 40, well, it's around 5,000 LUTs. Now, you don't want to ever like get to 100%. That designs don't ever actually use 100% of your resources because there's weird things that happen. So you do want to have a margin. But looking at the number of LUTs consumed by CSR, looking at the MSK top so far, maybe we got a chance of actually putting Opulent Voice into this project. Now, we don't have to do that because the goal of the project actually is to provide fast uplink, slower downlink for some of the more legacy, lower bandwidth, smaller bit rate modes. So, but anyway, I just wanted to show that this actually is in the ballpark, and Martin was very clear on wanting on orbit reconfiguration of their resources so that the FPGA could be reconfigured and that FunCube Plus could serve all sorts of different projects. So it was not clear to me that we could actually like do it, but now I think it's much more clear. So we're in the ballpark. We could do it. We could be maybe a project here and offer that along with the support for Martin's goals, which if you haven't seen the video from last week, he gave a fantastic presentation about it on the 11th. So yeah, that's something that we worked on this week, was to try to suss out and figure out exactly how many resources we're taking and where they were going. Another good thing that we found is that yes, our FIFOs, the first in, first out buffers for both receive and transmit, and also the circular buffer for the synchronization word search, they are successfully being assigned to BRAM. So they're not consuming the lookup tables, that's the kind of the short supply, the thing that you want to only spend when you have to. And the block RAM is being consumed successfully. There was a question. We did not get that to happen right off the bat, and we were a little bit worried about that. Also, our FIFOs are kind of big. They're very large, so that we can clearly see them in simulation and in hardware testing. Those are going to shrink down we're going to optimize those to say, okay, when you're going over the air in any particular situation you'd find yourself, that you only need this much for the FIFOs. And that will give us back at least some of the BRAM to maybe use on other things. Okay, I'm going to stop sharing that. And then what I'll do is I'm going to show you one more image, which is, I have to go make sure it's actually on the screen. And I'm going to show you what it actually looks like, what our implementation currently looks like on the Pluto. This is a really neat image. Okay, so what you should be seeing is a bunch of cyan or weird blue, green blocks, and the whole image is the Zinc 7010. So this is literally the implementation. This is a visualization of where all of those lookup tables, where the BRAM, where all of the resources are allocated. And I tried to get it to be color coded, but when you zoom all the way out, all the colors kind of blend together. So you can't see like what is the reference design and what is our custom code. But our custom code is kind of a lot. So our custom modem into the reference design, and when I say reference design, this is like the basic a basic software radio from Analog Devices provided for the 7010 on the Pluto SDR. So this is the smallest of all of the dev boards that we work with, because we also work with some like 7045s or 7100s and some ultra scales, which are much larger. This design would be a much smaller, but you can see with all of the reference design, all of the essentially the overhead or the infrastructure that has to be in the FPGA for the Pluto SDR to work, we've added R code and we still have some headroom here. That headroom is currently going to be taken up by randomization, forward error correction, and interleaving. And all of this will make our signal extremely resilient. Randomization makes the spectrum very efficient. Paul showed you what it looks like. It looks like lots of lobes that are just nice and full, clear, random looking, takes up every bit of space in the spectrum. It's a good thing. The forward error correction we've taken out a lot of redundancy in our signal, but we're putting back in redundancy that makes it to where we can detect and correct errors. Interleaving scrambles the bits with respect to time. Randomization scrambles them with respect to value, but interleaving moves everything around. So interleaving is key. It follows the forward error correction, and what it does in order to make your signal even more resilient to noise is that a burst error or a crash of static or something that happens that wipes out maybe many symbols, many bits in a row. When you interleave, the position of all those bits is all over the place. So what looks like a crash of static or a loss of signal, a dropout in time, when you get it into the receiver, you've rearranged all those bits, and those errors are now spread out all over the entire thing, and that is easier to correct. So those are two different ways. There's three different phases, and you can see this over and over again in all sorts of digital signal processing signals. This is uh, not uncommon at all. We're just kind of implementing it here and doing all of the process in the open and publishing absolutely everything and showing how it's optimized and why we picked what we picked. So all of that is going to have to fit in the dark space at the top. We'll see. We're working on this right now, and in simulation, it's starting to work and giving us like what you put in is what you get out. So there's all sorts of weird stuff that happens along the way. If we break the bank here, then all of these processes, the randomization and the forward error correction and the interleaving, are going to have to stay on the software side. So, like I said, when you have to balance one to the other, you have to decide what functions go into software versus the FPGA. Here's the FPGA as of today, pretty darn full, but we're going to go ahead and try to fit all this stuff in hardware. If it can't fit in hardware, it already exists in software. We already know how to do it and we're good. When we go to a bigger chip or a custom board, we'll put it back into hardware. So this gives us a lot of flexibility and it keeps the spirit of Matthew's modem module approach fully alive. So we're able to handle both cases. All right, so I think that's a good summary of the FPGA side and what we're kind of dealing with.
Yep.
Any, I'm going to stop and answer any questions or anybody that has any comments.
Well, I've got a comment. This might be a good time to insert something I forgot to mention, which is that I did a little quick benchmarking on processor utilization on the PS side, and I was a little worried that we'd been putting so much load on the processor, but it turns out it's a lot more powerful than I thought it was, and we're using a tiny percentage of the memory and only a few percent of the CPU to do what we're doing now, and that includes streaming out a whole mess of debug information that would not be used in production. So. Um, you may be running out of LUTs, but I've got plenty of CPU horsepower if I have to take up some slack.
Cool. Okay. And I know that there's some things that we talked about just this morning about moving some of the initial, like when you get a push to talk signal and you're told transmit, that the hardware needs to handle the preamble and things like that. And that's no problem. So we've been working on those sorts of situations as well.
What does the power consumption look like for that 7010
Oh,
in that
that's a really good
configuration?
question. Yeah, there's a power consumption estimator that Vivado provides, and they warn you that it's impossible to tell because you can you can definitely state with a lot of certainty what each individual module or in VHDL like which one of these chunks of code will what power they will consume when they're on. What it can't be predicted is when each of these sections of the FPGA are on. So, like when you look at a modem, you can say, okay, when it's on and transmitting, it consumes X watts or milliwatts, but it's not on 100% of the time or 0% of the time. It's on some percentage of the time. So you need that information in order to give you a real good answer, but it's in excess of, we already knew this because I think that you've already gone through, with your experience, with your background in looking at different FPGAs, you already know that like even the 7010 is when it's full on, both cores, everything's working, it's like approaching 2 watts of power. Um, but it's saying, oh, about a watt, 1.1 watts,
Yeah,
1.2, you know. So that from the estimator, from the crude estimator, then we can see where the power is being consumed. And when everything is on and transmitting, it's well over the half a watt that you would like to meet.
yeah. Another question would be, I'm not very familiar with the details of either of these FPGA architectures, but a loot in one FPGA architecture is not the same as a loot in another. Do you have any sense of how a 7010 loot compares to a an ICE40 loot?
Oh, that's an excellent question. And I actually meant to say that because I was like, oh, I know the loots for the 7010, but I don't know exactly how they match up to the ICE 40. I actually did mean to say that. So thank you very much for bringing that up. When we compare these sorts of things, it is going to be apples to oranges because each family of chips, even from the same manufacturer, like when you look at loots in one Xilinx family, they're not the same as the other. So I'll go back and make sure and I'll publish something or try to figure that out. In general, they're pretty close. At least in my experience, they've been pretty close. And especially for like I guess a lot of people consider the 7010 that's in the Pluto to be low end. And it's a 7000 series. It's not an ultra scale. So it's probably close. Um,
Yeah,
it's not going to be too like hugely far away, but you're right. It's not going to be exactly the same. Now, since it's the same numerically, doesn't mean it's going to be the same to implement, but it's not double or triple. It's close. And there is a lot of things that we have in the design, like the AXI streaming interfaces between, because we wanted to be modular, but modularity comes at a cost. When you make a design that's modular and flexible, you have to spend resources to make it flexible. So, taking our design, taking out all of the AXI streaming, reducing it down, like making it a monolithic design, I don't think it's 5,000 loots. Like take 2,300 loots out for configuration and status registers, keep the bare minimum that you need in order to configure it after you've gone through the development process and you know what you're doing. I don't think it's 5,000. I think it's much less. So a lot of that's the overhead of having a modular, flexible design. So I think we're definitely in the ballpark of being able to fit it in like something like a nice 40, which would be really cool. So we'll do what we can. And we'll also look at like, okay, how, like when we talked about the other day about the adaptive, noise cancellation process of digging out weak signal work that you would like to do. And it might not be total information awareness level, but we are going to get like a good couple of signals. Like it will be able to process things and we'll be able to achieve that. And I think that 5,000 ICE 40 lookup tables is going to be I think it's achievable. It'll be non-trivial, but it's in the ballpark. So I think we're good. I think we can keep proceeding and keep chipping away at it, and put our backs into it and get it done well before we have to start worrying about deadlines.
Yeah, I mean, you've really gone for an approach with this of putting as much as possible into the FPGA. I was thinking of it more from the other direction of, let's try and do this, in software on an ARM core and have the FPGA to offload particular things, where because the ARMs are, you can clock them at a few hundred megahertz and they can do a lot of DSP. Um, there there's a lot you can do with it, certainly at kilohertz bandwidths and so on. So it doesn't have to be a sort of all focused on the FPGA kind of approach here.
Yes, that's exactly right. We tend to be. I think probably Paul is a exception to this rule that we do tend to try to put everything possible into the FPGA, and the reason why you have to pick your battles. Like, okay, what can be put into the FPGA? What could you possibly offload to what is usually underutilized? Honestly, the FPGA in most software-defined radios is just doing decimation, and that's kind of a crime. So just put as much as you possibly can in there. What does it buy you? It buys you time in the general purpose processor, which can do all sorts of things that the FPGA cannot. So I think the vibe that you're feeling is because we really, really want to reserve the general purpose processor, like an ARM or whatever, the ARM cores, for doing things and making decisions and interacting with the actual real world that the FPGA can't. It just isn't very good at interacting with humans. It's very good at doing all of this amazing hardware stuff and a lot of DSP. And so, yes, you're right. The that critique is fully valid, and we are biased towards putting stuff into the FPGA. But in our defense, is to free stuff up. It's to free time on the general purpose processor to actually deal with the real world. So yeah, and I'm not I think I'm more familiar with like the ARM cores and the dev boards that we have than the part that you've picked, but we can come up to speed pretty fast and figure it out. And it's going to be
Yeah, well, as I say, that it's something that can be switched out. It's just STM32 is probably sort of the best known one that most people are familiar with, and it's that's the sort of top end of the performance range for those, and there's not really any point going less than that for putting it on a board because if you want to save power, you just do less stuff. Really, the consumption scales pretty directly with what you're doing with these things.
yeah.
The another thought. I mean, the reason I have a 5K LUT part on the design at the moment is specifically because that's the biggest one you can get in a QFN package. There is an 8K LUT set of those ICE40 parts, but they all come in a BGA package, and that's a concern for inspectability of the solder joints for flight hardware.
Right.
So that's why specifically what's on that design at the moment is the 5K.
Right. Yeah, that was clear. That's a very I'd say amongst people that actually are care about inspection, like physical inspection, and that do like Leo and above space. That's a well-known dividing line. So yeah, very
Yeah.
very well understood.
Okay. Um, I I wondered if you had any thoughts on what David sent about possible modes. Those specific BPSK up and down combinations.
Oh, I'm happy whatever David wants. Now,
Yeah.
now I'm on record.
Okay.
So yeah, whatever he wants in terms of like the up and down modes, I think he and other people at AMSAT UK are probably the best possible folks to have any sort of like the authority on like which modes matter to the community, which ones people would like to have supported. So um, yeah, I yes, I'm happy to.
From an implementation perspective, whether it's BPSK or MSK, really, the basic architecture of modem is going to be much the same, really, isn't it?
Yeah, a lot of it is.
Yeah.
Yeah. I see two kind of like big categories. And there's the weak signal work where you're essentially like interrogating the spectrum, right? And
Yep.
drawing out like where's the cool stuff. And that's one particular mode. And then the other is like, okay, loudest person I hear, I'm gonna translate it from this to that, so a more practical radio design or pragmatic, mode oriented versus, so the mode oriented stuff is one category, and then the stuff that you talked about last week is another, the weak signal work, kind of like finding interesting stuff that you don't know in advance, like you're not maybe not expecting it, and you would have to kind of identify the weak signals and properly draw them out. And to me, those are two different categories,
Yes. Yeah.
and
And
we can switch back and forth, but I think it's going to be a total different FPGA build for one or the
yes. Yeah.
other.
Yeah. So what came up in the meeting we had on Sunday was the thing about designs that have been done as part of FunCube 1 is many of those parts have since been flown on other missions as well. Um, and often those are piggybacked on some other satellites, so that if it's a bigger one, there's more power budget available. So there's a sort of approach here potentially where we have a sort of dev board platform that's got the analog front end side of things, um, through to baseband and ADCs and so on. But the specific combination of like processor and FPGA is something that might change depending on the mission, according to the power budget. Um, and then that's a sort of interesting architecture to have, because in a future mission with more power budget, you could fly more or less the same thing, but with more compute resources and do some of the things that we can't do in a 2U. I mean, the 2U is going to be the sort of bottom end. Um, what can you do on an ICE 40 kind of thing? It's not really going to do, as you said, the weak signal work. Um, but I think the one thing we would want to be able to improve on is the situation that happened with Green Cube, where it was just very hard to get into the satellite. And so if we could get 2 or 3 channels going, obviously that may be tricky given the LUT counts you've just sort of shown. But it opens a lot more, a lot more usability, to people trying to make contacts.
Oh yeah, that's a good point. That's a solid use case. And yeah, I think we can take note of that and then see what we can do. And that is a load balance issue because your processor can manage something like a bit slicing, right? A lot of these modes um, are, when you look at them, um, are not that heavy, not that hard in terms of bit rate. And if your FPGA can simply provide the processor bit slicing of all of these different strong signals, then there's your multiplexing right there.
Yeah, yeah,
And that definitely should be under our consideration. We should pay close attention to that because the use case, the hard lesson from Green Cube is that, like, you know, is we would like to make it that not happen. Like we'd like to address that particular issue, and I think that we can. I think that your comments about the processor versus the FPGA and the load balancing are really on point.
So one detail that isn't really clear in the dev board design yet is exactly how we're going to move data around between the processor and the FPGA. So we don't have that many pins on the FPGA if we're requiring a QFN package. So there's a question. So data comes in from the ADC in I2S form. So the FPGA could crunch that, pass it on to the processor. The way I've got it wired up on the board at the moment is that both chips have access to the I2S pins for both TX and RX. The other communication that's between the two parts at the moment is the SPI bus that's used for configuration and can also then be used for comms after that. But we don't with that part have much else to do, any sort of parallel bus between the two or any memory or anything like that. So I am wondering whether we might have to go to a higher pin count part just to be able to get that get some more form of interconnect between the two, like ideally like a memory mapped kind of interface or something.
Right. No, that's a really, really good point. This is, and what you've just described is like an eternal issue with FPGAs and general purpose processors because all of the tiers come from moving data around from one domain to the other. Like just even the clock domain crossings are a whole thing. That's why we have FIFOs in our design is they're dual clock FIFOs because the data is coming in from the processor side and has to get to the FPGA. Wow, what a ordeal. And yes, that's a huge issue that I think we should probably look at. I'm gonna say that the like the frame rates that we're talking about, the data that's shipping around and for most of the modes that we're talking about, that it's low enough to where as long as the FPGA processes everything and says, here's the data, like that baseband data, here you go, it delivers the baseband data, that actually isn't too bad. I don't know if it can be done of the existing interfaces, and I think I'm going to let Paul weigh in on that because he's way ahead of me on working with this sort of stuff in the past and has a real so I'll let him answer if he wants to. And this is also a reason why the Xilinx Zinc exists, putting a hard
Yeah.
processor like literally like embedding it in the FPGA fabric, and then of course then you have to pay more money and it pulls more current. But that's why they did it because it's like what a headache. It's a real
Yeah.
barrier to
Yeah.
us that when we want to do things and we want to shift things back and forth. So like the boundary crossing between the like the processor and the FPGA is always expensive and weird. With the number, if I had a penny for every undocumented weird ass thing that happened with this, then I'd not have to ever work again. So it was like it is a big issue. So we should absolutely look at it. My gut instinct is that because of the data rates we're talking about and because of the frame rates we're talking about, and we do actually have modes that bust things down to the baseband level and just ship over either voice or voice and data, that we're okay. I think we're okay. But you're right. That's something that we should probably check to make sure that it's not a deal breaker. And then do whatever we can to fix it. If it means going to more pins, then we go to more pins and, wouldn't be the first, non-inspectable part to go to. It always like makes you feel a lot better when you can actually see all the pins and make sure that they are solid before you send it up, especially, you know, I,
Yeah, well, I mean, there are techniques, X-ray inspection, and so on, that can be applied to that. It's just another cost to
yeah,
access that and so on. But
yeah, kind of a pain in.
uh, yeah,
Okay. Yeah, we should that's put it on the list and we'll track this as something to at least like get some basic reassurance. Like I think just my instincts are that the data rates are low enough to where we're good. Like
yeah.
it provide
Because
everything.
the thing is, this is the sort of detail that I need to know in order to finalize a design of the dev board and start making some hardware for people to play with.
Right.
So that's we can't really start doing things until we've got something there.
Right. Okay. Let's see what we can do. I'll try to
Yeah.
get on it. And I think we'll be able to maybe not give you like hertz accuracy, but we'll be able to tell you that it's achievable, like we're just looking for a minimum. And I think it's good, but we'll try to do our best to kind of ring it out.
I mean, the other possibility would be, put, VGAs on the dev board with plenty of pins and give us lots of options, and then we've got ways to do things.
Right.
And
That's always a good escape ramp.
yeah, which would be a change from what I've got on there at the moment. But as I say, the digital side is not really finalized in much way.
Okay, cool. All right. Anybody have any questions for Martin? Or Martin, do you have any other questions or reports for us?
I think I've covered what's on my mind. Thanks very much for what you've done. It's good to see that sort of concrete LUT count for something extant that works, to have a sort of point of reference. That's very helpful.
Yeah, happy to help. I'll keep working the reports. I'm sure this is just kind of scratching the surface. There's a lot of other stuff in there. But I think the main issues are, can you fit it onto the FPGA and does it consume too much power? And so that's what we'll continue to place at the highest priority. And we'll just keep working at it. Go ahead, Paul.
I don't have much to add, but except that from my physical touching of the Plutos during some tests, I know they use more power than Xilinx says, and I think it's probably the radio burning up all that power. So if we're micro optimizing the FPGA, we might not be on the right track for
Yeah.
overall power budget. I don't know. I haven't tracked that down. I don't know what the actual numbers are or where the power is really going, but that's what it seems like to me.
Yeah, the all I have is the estimates from Vivado about how the chip acts. They're usually pretty good, but again, they don't have anything about duty cycle or yeah, this is why when I did ASIC design, you spend a lot of time with power consumption, turning things off, and you're really aggressive about it. This is exactly why. So we're going to have to use some of that same attitude here to reduce the power consumption. If you have any way to kind of measure like a watt meter, or I know we have a power meter in the lab, and if there's any way to kind of like sneak that in and see what we're actually consuming with Opulent Voice, that would be actually really helpful. Then we can compare it to what both analog devices and what Xilinx say.
Yeah, I can measure the overall consumption of the Pluto, but I have no access to individual breakdowns of which device is using the power.
That's okay. An overall number would give us a good reference.
Well,
It's
I can
like,
give you an upper bound right
yeah,
away. It doesn't use more than a USB port worth, so
that's
two and a
good.
half watts.
Okay, that's good. Well, thank you so much. I'm looking forward to plowing into this. It's reminding me of cellular phone development. So it's the same set of similar or same set of concerns with the battery powered terrestrial stuff. Awesome. Well, thank you so much, Martin. I'm looking forward to pushing this along and making it as successful as possible. Thank you so much for your volunteerism and and all of your expertise, and uh, all the work that you've been doing over the past couple of years. For folks that want to keep up with this, it's AMSAT UK, United Kingdom. AMSAT stands for Amateur Satellite, and AMSAT UK is the premier organization in the UK for amateur satellite work. And they have a very successful FunCube satellite. If you have heard of this, you may have heard of the FunCube dongle, which is a really fun SDR in its own right that has lots of use terrestrially as well as for space. And we're very excited to support this and to try to make it as good as possible. And yeah, we'll be chipping away at this every week, and trying to spread the word and get folks to learn more about amateur satellite and amateur astronomy, amateur radio in general and for the digital signal processing side, this is actually a really, really good project if you are wanting to learn about FPGA and contribute to an actual project that's going to launch. It's a really good opportunity. So thank you so much, Martin. Just let me know if you need anything else.
Yeah, thank you. It's amazing to have other people interested in this project because this really started out as me coming in with some crazy ideas to the FunCube folks, and not really being able to follow through on them. Yeah, I've always said I'm not precious about it. This is something I'd like to be a community thing. So I it's wonderful to see other folks wanting to get involved.
Yeah, we'll try to grow this particular group and get some additional horsepower. So thank you so
Yep.
much. Awesome. And I'd like to welcome Oscar, who I think some of y'all know Oscar from the University of Puerto Rico. And we've had lots of interaction, very positive with the University of Puerto Rico, with previous versions of Opulent Voice on sounding rockets. And Oscar, you got the floor. Tell us anything you like and any questions you have, anything that we can possibly help with.
Hi, I hope you can hear me. I just test the microphone right now. I can see that it's coming up. Anyway, nice to meet you guys, Martin. Paul, again to see you, and Rick, and of course Michelle. Something that resonates very strongly. We're working into a student sounding rocket, and it resonates every single time. It is data transmission from space. It is even trying to get with Iridium and things like that. They're not so reliable. You can work out with the NASA telemetry that works quite well. They have several stations in parallel and at the same time several bands, and they record every single bit and in one single stream, and that works quite well. Now, what about when you are by yourself? What about when you have students making a CubeSat? What about when you have students making a sounding rocket payload? There's a lot of failures. There is even probably experience in RF, probably out of experience of how to do things properly. And that is exactly the question. How can we have a reliable communication? And this happens, last August, we had a flight, which we were testing, and I have a short video I can show you if somebody wants to see it, or it can be sent to you guys. And don't waste the time here, but you can see it any time. They have two commercial grade transmission for the small CubeSat for testing, and it happens to be that we have the third one by Opulent Voice, and our works. And we were before launch getting this data transmission, and during flight, and even spinning, and during actually all the rocket alignment and pointing and things like that. Even when it was out of pointing, we were collecting data. And not only voice, we need data, transmit data as well. This is one of the big highlights that we are learning. If it can be embedded into the voice, the data, or even transmit data, very reliable data, that is an asset. And this is not only for amateur, not only for standard communication. This is also for multipath and farther away. I mean, signals. And I'm sure you know more than I can explain myself as the experience that we're gathering. So there are these universities are asking for help. They are actually asking for help how to get their data being transmitted downlink and to be reliable. And this is the big question. And definitely my experience with Opulent Voice have been great. They have been proven to work on space. And this is actually the video that if you want, I can play it for you so you can see it. And I believe it's about a couple minutes or 4 minutes, I remember now. But data and reliable data with the forward error correction, with the interlace and the scramble, that make it happen. I did overpowered. I can tell you, I have a 8 watts output. Probably I can do it with 1 or even half of it, but I wanted to be sure that I have enough power that I can recorded during the whole flight, and we did record it. We did receive the information. Barely, I have somehow have to go back and see what are the errors on the file. So anyway, this is my name is Oscar Resto. I work for the University of Puerto Rico. I'm a physicist, a ham radio as well, KP4 radio Fox. And I do experiments in sounding rocket. Today, actually, by chance, it was my 21st flight into Andoya, Norway, looking for habitability signals and measuring the magnetic fields and concentration of water and ammonia at altitude of 250 kilometers. And today we have the flight at 6:07 this morning, actually my 21st flight. So back to you, Michelle, and nice to meet you guys.
Wow, thank you so much. Yeah, no, you've done many missions with students, and your perspective is incredibly valuable. So yeah, when we're talking about resilient signals that are very protected against all of the horrible things that might happen to them along the way, there are some things that we do. We take out all the extra stuff. So, you know, before it even gets sent, we treat the audio or the data, you know, whether it's keyboard data or a file, or if it's readings from sensors, you know, because when we talk about telemetry from space, it might be sensor readings, the health of the spacecraft, super important, things like that. And we want this information to get back to Earth exactly the way that it was sent. So we take out anything extra, any redundancies, extra data, and we get exactly what we need, packed in as tight as possible. But if we sent that, then it would be a disaster. So just because it's efficient, it's all packed together, any noise would harm it. So we put in a whole bunch of redundancy. But, you know, people have spent decades trying to figure out exactly what kind of redundancy we want, and we've gotten pretty good at this. So we're good. And one of the reasons that Opulent Voice works as well as it does is because it has pretty much the best you can get. It's optimized all along the way for the bandwidths that we are using, for the bit rates we're using. And we're always kind of looking for more. You know, is there anything that we can do to improve it? There is a physical limit. So this doesn't not, you can't just keep adding redundancy and then expect to get more. There actually is a limit. You can only get so good. The good news is that we know what that limit is, and we're really close to it. So that's kind of the good news. And the bad news is that, well, it's kind of complicated and quirky and tricky, and you know, then you have to pick the right part. So you know, everything that Martin is talking about, that we've been talking about in terms of like load balancing between different types of processors, or picking the part, you know, that's good enough, is one of those things along the way. So if there's anything that we can do to make it better or easier for downlink, you know, when we're talking about from a spacecraft back down to Earth, you know, and it's not just the link and the communications link, but usually these things are moving, and that adds Doppler into this, which is different. That causes all sorts of weird issues. So there's all sorts of digital signal processing techniques that work for Doppler that give you advantages there, that you might not use if it's a point-to-point link. You know, so the good news is that, like, at least Opulent Voice, it's kind of picked for Doppler environments, and it's already set up pretty good for it. And that's one of the reasons why it works okay for that. So yeah, I don't know. Back to you, Oscar. Is there anything in particular that you want to achieve, or is there anybody that we need to talk to or help out?
To whom you make the question?
Oh, you. Yeah. Is there a question in particular,
Yes.
or a problem?
Yes,
or
I would send you a couple of emails, people that are requesting for help. And I will do that on Thursday. I will send you emails of universities that are asking for help.
Okay.
And I think that would be a great opportunity. Really, one of the things that I have to remind you, not only the Doppler, the rocket goes spinning about 5 hertz. So even through the spinning, we were getting signals without any problem.
That's right.
That was amazing.
Yeah,
that was really, really amazing.
Yeah, the video, I think, because you have it's not just one video, but several videos that shows I don't know if any, I'm sure that some of you, like, I know Paul has seen this, and I'm pretty sure Martin's seen it. I'm pretty sure Rick has seen it. Like, when you're on a sounding rocket, it's violent. It is because sounding rockets don't have people on them. They don't have to worry about the people, but they like spin and stuff, and the spin rate and the G forces and the speed was just incredible. So, if you have not seen an onboard video of some of these experiments from a sounding rocket, it's pretty amazing. And yeah, the spin is a that's additional Doppler. That's not just the movement of the
Mm-hmm.
rocket, but it adds a little oscillation back and forth. We see the same thing in EVE, so the Earth, Venus, Earth. Like there's when you're on the surface of the Earth and you're trying to communicate bounce signals off of something like Venus, and you're looking at the interaction between Venus and Earth, there is this extra oscillation because you're on the surface of the Earth. This adds or subtracts from the Doppler that you're already experiencing, and it's a real deal. A lot of times when you're just approaching these sorts of problems and you model it from like the center of the body, from the center of the earth to the center of Venus, there's no such thing. Like you don't see the problems. Then when you put your station, on the surface of the earth and you are bouncing off the surface of another planet, all of a sudden you see these severe Doppler forces. They really mess things up. And that's the same thing for the satellites. Spin stabilization is a big deal. And yeah, the sounding rockets, they spin like crazy. It was really remarkable. So, what I'll do is I'll share when we publish this video. I'm going to post the links that I have to the stuff that because it's really well worth seeing. You get to see firsthand what it's like for the little radio inside of a sounding rocket. It's remarkable.
And by the way, we work together as partners and for the last 2 years, and we're looking forward for more events. And the support have been really great from Paul, from Michelle, right on target, and the students have been enthusiastic and with the free time they put their heart on it and they make it happen. The video will show that clearly. Nadia, we made it, jumping and so happy. So this also helps for ham radio community to bring out the youngsters and the professionals into it. So this is part of the whole thing. I mean, we can make experiments. And by the way, we did have an experimental license to get it on the Sounding Rocket. We didn't hide. We put it openly into the FCC. So we did have an experimental license. So we were successful doing it as well. Back to you, Michelle.
Yeah, no, that was a very good outcome, and your students are amazing, and it's a real privilege and an honor to be able to help in any way. So yeah, count us in as long as you want us to pitch in. We'll be happy to keep.
And by the way, for this mission, let's call it that way, they need to test something in a sounding rocket, a test bed. We are trying to fly a rocket onto, I don't know until when, but at least one more year. If you want to try a device and put it into space and get it in a rocket environment and actually get some data within the 10 minutes of flight and so on. The whole flight's about 15 minutes, but get it on space and get it into the 20 Gs, 50 Gs impulse and so on, and get it over 160 kilometer altitude and get the information downstream things. It can be done. It's called RockSat. It's called RockSat. It's on NASA. But at the same time, they're looking for people from like institution. I mean, non-commercial ones. And so these are the real place for the experiment. As well, if we have the experience of doing it, we can help you guide it, or I don't know what. So we can open this kind of doors.
Awesome. Yeah. No, yeah, I think we'll take you up on it. There's several different things I can think of. So thank you so much, Oscar. It's a real honor to work with you. Cool. Okay. Rick, hey, the floor is yours. If you'd like to bring us up to date, tell us anything that's going on with you and anything that you need.
Oh, well, we are still working on the drift scan experiment at DSES. And fortunately, I've gotten a lot more support in the last few weeks. We had an interruption because of the ARRL EME contest, but fortunately, as soon as the contest was over, the hydrogen line feed was reinstalled within hours, and I'm back up and running. We're still trying to find the magic uh, combination of the right data collection software with the right front ends. So I think I mentioned before, the last time I was down there, I modified the architecture somewhat so that the 1.42 gigahertz feeds into a wideband low noise amplifier that comes down to the control center, where there's another 10 dB gain block feeding a 3 dB splitter, and that is now feeding two different receivers. The the dual, I can't remember, the Aerospy Duo, I think it is, and the Edis B210 are both being fed, and they both go to USB ports on the Linux computer, so that theoretically, I can switch between those receivers and try to determine which is more appropriate for our experiment. So far, I have not used the B210 at all, but I will be doing that soon because we have a new data collection software module for the B210 that I'm going to try. So it's all going very smoothly so far. It's just I haven't quite got it to where I'm satisfied that it's the best I can do. Once I have that done, then we will start a scan of the universe from plus to minus 40 or 20 degrees uh, from the zenith. Uh, Beyond that, we have to steer it manually because we can't leave it parked any more than 20 degrees off the zenith because of the severe weather we get out there. And it's a pretty big antenna. So, but that's okay because if with a beam width of 1 degree or so at that frequency, that's 40 different settings. That means 40 different trips to Haswell. That should take about 2 years.
Right. Very good.
So in any case, anyone who would like to see what we're doing down there is welcome. I'll be happy to drive him down and show him around at Haswell. You just have to allocate a full day if you're leaving from Colorado Springs, so you have to have travel time to get here first. But I'd love to show people around.
And for anybody curious about what DSES means, it stands for Deep Space Exploration Society. And I think it's dses.org is the website, Rick?
No, actually not. It's dses.science.
Oh, very good. dses.science.
There are too many DSESs out there.
Yeah, no kidding. And you know a little bit about the website because you've done some work on it.
Oh, yes, I have been adding new sections, one called projects that lists all the primary projects we're working on, what their background is, and some of the reports. And we also do pulsar magnetar kind of work, detecting pulsars. And I have done a huge update to that, which is under the section science. And we now have reports dating back for years. The more recent reports are very complete. The other ones are snapshots of the results dating back through every pulsar we've ever detected, which I think is up in the mid-20s somewhere of pulsars. So the science section's been updated and the project section's been created out of thin air. So yeah, I put a little bit of work in to inform people of the kinds of things that are happening or should be happening down there.
Yeah, very good. Outstanding.
Now that we have a fiber optic link at the site, uh, if anyone has projects that they would like to use a large antenna for, and are only available to operate them remotely, we can discuss those. Because we can do a lot of remote operation. We just do not allow steering of the dish without two people on site. But
Yeah.
even then, even with that, we often have people on site doing routine maintenance. So if you have a project that needs the antenna steered, we can schedule that.
Yeah. No, I think you need eyes on anytime you're physically moving something with, it's just too much risk to do it remotely.
Yeah, it's a little large. We
Yeah.
are working on uh, we are working on putting up a smaller 30-foot dish, which we expect will be allowed to be remotely controlled when we get that done. And we've had some good success recently uh, in terms of fundraising. We've had some large donations come in. That was a big surprise. And we're hoping the more people who look at what we're doing and see value in it, uh, the more we'll get people to join. That's one way to donate some funds or have their foundations donate, which we've had. So things are looking very good right now.
Awesome. No, that's all good news. All right. So yeah, DSES.science, and it's a big dish doing a lot of work. And yeah, looking forward to the next year or two because there's a lot of cool events coming, and with all of the big steps forward in terms of infrastructure at the site, getting much better digital communicate. Well, not digital, but communications, getting a good infrastructure in for internet access. That's a big deal. That's going to open up a lot of things.
And I'm looking forward to transmitting opulent voice signals through that antenna one of these days.
Yeah, I think we're super close to that.
We will have no trouble reaching your West Coast lab off the moon.
Yeah,
Uh,
I bet not.
our signal off the moon is what we call 5.9.
Yeah, I think the EME contest, they know you're there, right?
And yes, yes.
Very good. Awesome. Okay, any last comments before we close, Rick?
No?
Cool. All right. Well, thank you, everybody. This is we really, really appreciate your time and your attention, your expertise, all of your just a wealth of information and wonderful things that we're doing. We know that once you spend the time, it's gone, so therefore it's priceless. So we really, really appreciate everything that you're doing, and we just hope to keep working on things like this and helping good things happen. So thank you so much, and we should be here. We should be here next week. We'll probably take off for the week of United States Thanksgiving. Oh wait, that is next week, I think. So we might be take off next week. I'll put out an announcement. We may take off for Christmas, but we'll be here for you. And we are looking to kind of like maybe have a regular meeting for the mode dynamic transponder for the AMSAT UK project because that's a whole body of work that involves some systems engineering and some looking at all the things we talked about today. So just keep an eye out for potential meetups. We're going to try to make it to where it's very friendly for the leads and principals of the team that are in the UK. So we're looking at kind of doing that, or alternatively, if there's existing meetings, then be more involved with that. So just trying to get some more communications going and some repositories of work set up above and beyond what we've done. I think our initial analysis, the Python for the up down, just like what you're looking at Leo, that's already published, but there's still, as you heard today, there's a whole lot more to talk about and to figure out and to document so that no one has to wonder in the future. So yeah, see you off and on throughout the rest of November and December. And then yeah, looking forward to the new year. Oh yeah, that was one thing that was on the list. We had a talk accepted about our work for Opulent Voice for FOSDEM, which is a open source developers from Europe. That's a European show. It's in Brussels this year. It's on the 31st of January and the 1st of February. We're looking for a speaker because it turns out it's an in-person only event. They did offer to kind of like make it possible for us to give a remote presentation. I would really like to avoid doing that if the event is in person. So if you are anywhere near Brussels and you can go and present about Opulent Voice and our work and would like to give your take on it, then just let me know because we would be happy to help defray the costs and to make it a pleasant experience for you to go enjoy FOSDEM and to talk about Opulent Voice. So get in touch. And I think that's it. So thank you, everybody, and see you soon.
Bye.
Bye-bye.
Thanks, folks. Talk to you soon. Bye.
See you soon.